Okay, so we were dealing with again same old biasing common source amplifiers, but without the use of without an use of a battery in series, right? So what we essentially said is, you have a network and this network puts out some independent voltages in the sense that it has its own DC voltages, some VDCQ plus VI, where VI is a sinusoidal excitation, and you have a common source amplifier which you want to bias, then obviously you will require some DC voltage at the gate, between the gate and the source. And if it need not necessarily be that VDCQ will be equal to that DC voltage that you want. So then we said that we'll put a battery. Then we found that putting a battery is not probably a very practical solution. Then we said that an infinitely large capacitance is equivalent to a battery. So then we put a very large capacitance. But the issue was that we need to ensure that both the plates of these capacitors are charged to appropriate value. And in order to do that, we obviously need some battery. But again, everything has to be derived from a master battery, which let's assume is VDD, which is 3 volt or 5 volt or something that will be given to you. So if that is the case, what we can do is we can simply voltage divide here and say this is R1, R2, and we can ensure that the division ratio is such that the VGSQ that is required for this transistor M2 to work properly is satisfied. Now, why does this this contraption work? This works because, in a nutshell, you can isolate the DC from between the two stages, right? The capacitor gives you infinite impedance at DC, 1 over omega naught C. Omega naught is 0 at DC. So the capacitor gives you infinite impedance at DC, which means that there will be no DC current flow between these two stages, which essentially means that you should be, in principle, you should be able to set the voltages at either side of the capacitor plates independently of each other. Now, that is all fine, but then we also said that we need to ensure the excitation, sinusoidal excitation VI, should almost appear without attenuation on the other side, because ultimately that is what my signal is. And we would want to ensure that the signal propagates without any attenuation from one stage to other. So in order to do that, what constraint do I need to satisfy? I need to satisfy that the impedance of this capacitor, right, at the signal frequency of, let's say this is VP, VI is VP sine omega naught T. So all we are saying is, in order for this condition to be satisfied, that is both sides of the capacitor plate should see almost identical excursions of signals, then the condition that needs to be satisfied is the impedance offered by this capacitor should be much lesser than the impedance that we see looking into the network that follows the capacitor, right? So essentially what we are saying is, if you have these networks, now we are only talking about AC, so this goes grounded, this goes grounded, and I am looking from this side. When I am trying to figure out the impedance from this side, what is the Z equivalent? Z equivalent is 1 over SC plus R1 parallel R2, right? So 1 over SC is the impedance given by the capacitor, and R1 parallel R2 is the impedance given by offered by the resistive network. So if we have to ensure that when we excite this node with Vp sine omega naught T, And we are saying that this is almost equal to Vp sine omega naught t, because this is this is our design requirement. Then in a nutshell, what we are essentially saying is that at the signal frequency, 1 over SC, right, the mod of 1 over SC has to be much lesser than the parallel combination of R1 parallel, right? So the constraint that we see in this case is 1 over SC has to be, this is at omega equal to omega naught, has to be mod of this much lesser than R1 parallel R2. And from there you get essentially the constraint that this R1 parallel R2 is some resistance. So essentially the constraint that you get is R1 parallel R2 times C should be much greater than 1 over omega. Now you should be able to appreciate this straight away by looking at this. Is this C times R1 parallel R2 is essentially the time constant of this network, right? What is the order of this system? First order, second order, third order. Do you understand what is meant by order of a system? Yes, right. So essentially, if I write a differential, it's a first order, right? So why do you say it's a first order? Okay, so in principle, even though that is true in this case, that did not necessarily be the case all the time. Because when you say that order of a system is equivalent to the number of differential equations, you are implicitly saying that it's equivalent to number of independent differential equations, right? If there are two dependent, if you can derive a third differential equation, which is some linear combination of the other two differential equations, then obviously the order of the system is not 3, right? So essentially, it has to be independent differential equations. Now, when you write it and write out differential equations, it's easy to figure out whether it's a linear combination or not. You essentially set a determinant and see whether determinant goes to 0 and all those things. There are multiple mathematical techniques. But how do we figure out whether a system is, looking at a system, can I figure out whether a system has, how many independent differential equations should we have? Now, as he pointed out, that one way to look at it is say that, I mean, if we have capacitors and inductors, each of them will give rise to some current voltage equations, which are essentially differential equations, right? Capacitor integrates, inductor differentiates, but if you can write out a differential equation based on each of these current voltage relationship of each of these capacitors and inductors. Now, assume that you have been able to write it out, but then the question is, how do you figure out whether each of these differential equations are independent or not? So when you have differential equations, when you solve them, you also require an initial condition, right? You need a plus C terms will come, right? So you need essentially initial conditions. So as it turns out, you can show that in a network, so in electrical network, initial conditions are associated with the capacitor voltages and inductor currents, correct? So if you have n number of different independent differential equations, you should be able to have n number of different initial conditions, right? So differential equations are difficult to figure out looking at a circuit. You have to write it down, but initial conditions are not difficult to figure out. So the hack that we circuit designers use is to look at a circuit and say, whether can I set n number of independent differential number of different independent initial conditions. If I am able to set n number of different initial conditions, then the order of the system is n. Yes.
So can any linear differential equation that help of
Yes, you can, right? So in fact, there is a whole branch of, there are some groups in the world who work on solving differential equations using circuits, right? So I don't know whether you follow the news, but there was some news flow saying that you can design analog computers for specific applications, not general purpose applications, which can perform certain differential equations solving tasks faster than the normal computers. Right. So essentially, you can design circuits which can give you real-time outputs, Right? So without going into numerical approximation. But those are specific things. But anyhow, so looking into this circuit, you can see that there is one capacitor, trivial example. You can set a independent initial condition on that particular capacitor. Now, I mean, why is this independence useful? I mean, another trivial example is, let's say I have this first order system, no problem. So this C, let's say I break up into C by 2, C by 2. Right, I can do that. Two capacitors. Doesn't necessarily mean it's a second order system. Right? Two capacitors in parallel can be clubbed into one capacitor, but in terms of the logic that I just said, you can easily appreciate that you cannot set independent initial conditions on these two capacitors. If you set it across one, the other gets automatically set. So essentially the order of the system is not two, it's not the number of capacitors, it's the number of independent initial conditions. Okay, fine. So now if you have a first order system, almost all the characteristics of a first order system can be associated with this thing called time constant. Right? So if you give a step input, to an RC network, let's say I give a step input here, I know that what will be the response across the capacitor, right? What will it look like? It will be something like this. What will be the equation of this?
CV into 1 minus C for minus 2 by tau.
Yeah, so essentially, this will be final value, right? So let me. So let's say this is a step of value 2 volt. Okay. So what will be the after t equal to infinity, what will be the voltage across the capacitor? 2 volts, right? Right. So average current through the capacitor has to be 0, right? So if this is 2 volt at time t equal to infinity, this also has to be 2 volt. Correct? So this has to be 2 volt at time t equal to infinity. What does it start from at time t equal to 0? 0. So it has to go from 0 to 2 volt. Now we are interested in the track. How does it go from 0 to 2 volt? So not a parabola, right? So if you solve this, it's a first order linear differential equation, right? You always get e to the power minus that form, right? And this will be, so this will be that this trajectory is essentially you can figure out by saying that this is equal to or rather let me say VCT. VCT is this final voltage 2 volt 1 minus e to the power minus t by tau, where tau is RC. You have done this? Right? Okay. So in any first order circuit, this time constant RC is a very vital thing, right? It captures the dynamics of the circuit, right? How if you want the circuit to settle very fast, which essentially means that if in this case my input is this, but the output has reached 2 volt at time, output is very sluggish the way it's moving, right? So if I want the output to go like this, what should I do? What change should I do to the circuit? Tau should decrease, right? So essentially the product of R and C is that matters, right? So intuitively it should make sense. How is the capacitor getting charged? It's getting charged by the current that is flowing from source to the capacitor, right? So if the capacitor is getting charged by the current, then the rate at which the capacitor will get charged is also dependent on how large the current is. Make sense? And if R is very high, as compared to R to be very low, what do you think is that, in which case the charging current will be higher? let's say I say that for a fixed value of capacitor, R equal to 1 meg, and another case R equal to 1 K. So the charging current will be higher in case of R equal to 1 meg or R equal to 1 K. Let's say at any instant of time. 1 K, right? So I mean, consider the time at t equal to 0. At time t equal to 0, voltage across the capacitor is 0. What will be the current through the resistor at t equal to 0? 2 volt by 1 K or 2 volt by 1 meg, right? It will either be 2 milliamps or 2 microamps, depending upon what R is. Correct. So naturally, the capacitor will charge fast when you have larger current, right? So for a fixed value of capacitor, the value of R determines how fast the system is responding. Correct? Make sense? So similarly, for a fixed value, did I say fixed value of R? So the fixed value of capacitance, the value of R determines how fast the system is responding. Similarly, for a fixed value of R, if I increase the capacitance, what am I essentially saying? Increasing capacitance means what? I need more charge to go to the same voltage. Correct? Q equal to CV. If I have to reach some finite voltage V, if the capacitor is large, then I need more charge to be dumped. Make sense? Now, if R is the same and I need more charge to be dumped, which means if the value of capacitance is high, I need more current, right? Or if the current is fixed, I need to wait for more time. Correct? So if I keep R to be same, then let's say at time t equal to 0, current is V by R. Do you agree? Current is V by R. So the slope with which this curve will rise is dependent on the current and also the rate at which the capacitor is charging. So in a nutshell, if the capacitance is high, it requires longer time to reach its final voltage, or in this case, it requires infinite time in any case. But for any, if you try to observe the system at any particular point, you will see that if the capacitance is high for a fixed value of R, the system will be far away from its final voltage than when the capacitor is low. And also when for a fixed value of capacitance, if R is high, then the system will be more sluggish, essentially, right? So in a nutshell, the time constant of the system captures the dynamics of a first order RC network. So essentially, all these networks that you will see for a fair amount of time in this course will either be first order system, or we will try to modify the argument in such a way that we encapsulate the behavior of the system using bunch of first order systems. Okay, so the understanding the response of a first order system is very critical. Okay, fine. So now tell me one thing. I just flip the input and the output. I mean, I just flip the position of the input and I say that this is what I will apply. Yes. Right.
Because I think that, for example, what we do in E200, we used to make slightly certain equations. Those equations used to have a d by dt. So we should combine all of them to make one common d.
Yes, but that will not be a first order equation. That bit common.
Generally, because before when you start from the concept of
right.
So I think those equations because you'll be using them to regulate how they independent.
Okay. So see the voltage through I mean, if you write, so the current through this capacitor and the voltage across the capacitor is related by relation, right? So you go through the mesh and you you get one equation. Correct. So now if you have, I mean, another example, the trivial example is this, right? In this case, if I say that I will try to write the equation, the current voltage relationship across the capacitor on the left and the capacitor on the right, they will not be independent, right? So how do I mean, looking at the circuit, how do I ensure that they are not independent? In this case, it's trivial, right? Sometimes it's not so trivial. So in looking at the circuit, then how do I ensure that it is independent? What I am trying to get at here is, when you have differential equations, each of them are associated with an initial condition. The initial condition is a hack to figure out whether it's independent or not, because if it's not an independent equation, I'll not be able to set n number of independent initial conditions. That's all, right? So instead of writing out, when you are looking at a circuit, I would like to write as less differential equations as possible. But we need to find out what is the order of the system. So the hack is find out, looking at the circuit, I can figure out how many initial conditions that I can set. So that is the hack.
Like in this case, we can say that the initial condition that the capacitor voltage initially was 0.
Whatever, 0, 1, whatever. But if you set 1, the other gets set. That's all it means. Right? Make sense? Okay. Okay, so let's take it offline. Okay. After the class, let's talk about it. Okay, so now let's say we come up with this circuit. I mean, not come up, but let's say I give you this circuit, and I ask you, I give a sinusoid here, right? I give a sinusoid here at omega naught, and I say the C is infinitely large. Okay, the C is infinitely large. What would you expect the voltage across the capacitor to be? Right? What will you expect the voltage at this node to be? That drop, correct? Great. So now let's turn our attention to the circuit at hand. So this is VDC plus VDC I can set to 0 for this purpose, right? So essentially what I say is I'll do this. So this is 5 volt. Let's say this is 2K, this is 3K. So this voltage is 3 volt. And let's say VI equal to VP sine omega t. Okay. So now tell me what is the total voltage across the capacitance if C is infinitely large. Or I can as well say this side. It doesn't really matter. Polarities. Right. Always 3 volt, or do you have a sine omega component also? There wouldn't be. So essentially the voltage across the capacitance is equal to 3 volt. Do you see? Do all of you agree? Right? No issues? Okay, so this is an important concept, right? Just because when you see a capacitor, don't assume infinitely large, don't assume that the voltage at one of the plates is always 0. Because sometimes what happens is, in this case, if let's assume this is Vp sine omega t, and the capacitor is infinitely large, what will be the voltage at this plate? It will be 0. It will be 0, right? So obviously it's easy to see because capacitor at very high frequency is a short, right? Capacitor at very high frequency is a short, which means the voltage across the capacitor has to be 0. So the more intuitive way of thinking is, this plate is not, the voltage value of that plate is not moving, right? The voltage attached to that plate is not moving, and the infinitely large capacitance is not allowing the other plate to move as well. Right? So if the voltage at this plate would have moved, then by principle of the fact that the voltage across the capacitor cannot change, this plate would have moved. So that is what that is happening in the circuit in the left. That is, if this is, since this is moving, the infinitely large capacitance is trying to force the other plate to move, while ensuring that the DC voltage across the capacitance doesn't change. So with this in perspective, we talked about Bode plot in the last class, and the Bode plot essentially is nothing but a plot of the frequency response of your network when you are changing the frequency. In other words, in this case, if this is VI, this is VG, Bode plot is the plot of VG over VI 20 log of this when I am changing the input frequency. So for obviously, when you do this, you need to know the equation with respect to omega, right? Otherwise, it's difficult to sketch a plot. But fortunately, this is a first order system. Since it's a first order system, we can easily figure it out. So in this case, what will be VG over VI? VG omega j omega by VI j omega, or VG over, let's do it in terms of in the S domain, Laplace domain. Should be more careful with the notations. Since I am going into Laplace domain, I should change. Okay, so what will be VGS over VIS? Is the question clear? What is the Laplace equivalent of a capacitor? What will you replace the capacitor with? 1 over SC. You know this or don't know this? No? Okay, so there I'll not go there. Okay, so maybe I'll. Yeah, okay, true. You didn't do Laplace equivalent in 200? Okay, fine. So maybe I'll take another class for that. So let's stick to 1 over j omega case, right? So you are comfortable with this, right? That when input is a sine wave at some frequency omega, I can replace the capacitance with 1 by j omega c, and R means R. This is fine. So if this is the case, then obviously the frequency at, this is VG and this is VI. So VG over VI is j omega c R by 1 plus j omega c R, right? So if I plot this, if I plot mod of this, right? Mod of VG over VI is omega RC by 1 plus omega R squared C squared, right? So if I plot this, what do I see? I can break this plot into two parts. That is, I say that at omega much less than 1 over RC, right? This mod of VG over VI is approximately equal to omega RC. Make sense? Do you agree? And at omega much greater than 1 over omega RC, mod VG over VI is almost equal to 1 by omega RC. Or sorry, in this case 1. Right? So this comes out basically with just looking at the equation, right? So since this 1 over RC seems to be some critical breakpoint, what Bode said was, to make our life simpler, we'll just say that since this is a first order system, the pole associated with the first order system is essentially 1 over omega RC, or rather 1 over RC. And if you are not comfortable with the concept of pole, but you just, in this case, you assume that, in this case, it's easy to see that 1 over RC is some sort of critical breakpoint, before which the system behaves something like VG over VI is omega RC, and above this location, your system behaves like it's almost the gain of 1. Correct? So what Bode said that I understand the system will behave like this when I am far away from 1 over omega RC, and the system will behave like this when I am far below omega RC. But then we don't need to bother about, I mean, obviously the system will not behave like these near 1 over RC, but for the sake of simplicity, we'll assume that this goes straight up, breaks, and this is what's going to happen. In reality, obviously, we understand this should be a much gradual slope, but in order to understand how the system works, mostly this straight line approximations of our frequency response is something that we live with. And as it turns out, even this gross simplification helps us a lot in understanding how a system works. Okay, so yes. Okay, just set this to be much less than 1. You get omega RC. Set that to be much greater than 1. You get 1, right? So omega RC much greater than 1 is equivalent to omega much greater than RC, right? So this becomes this, right? So okay. So now this Bode plot is an extremely useful tool because let's say, okay, I ask you to go to the lab and find out experimentally the response of this first order network, and I give you a box which can give you sinusoids of different frequency, and obviously you have CRO or oscilloscope to figure out what the response is. So what will be your strategy? So I want you to find out this Bode plot experimentally. Okay. So you go to the lab, to take this first order circuit, hook it up in the breadboard. How will you figure out this Bode plot experimentally? You need not necessarily start with very high frequency, right? So Bode plot is essentially plotting from all the way from 0 to a very high frequency, right? You set the frequency of your input to 0 and you observe what you get in the oscilloscope, right? One data point. Then you set it to some higher value, check another data point, and keep on seeing the amplitude of the output as you keep on changing the frequency, right? And you keep on plotting, you will get a plot. That essentially is a magnitude response of the frequency, right? A magnitude response of the system. And that when you approximate with straight line segment, you say that this is Bode plot. And the critical thing is at 1 over RC, so when you do that, you will get something, this magenta slope, magenta curve. So then where do you set, say that if I have to do this Bode approximation, where do I set, you don't know what is RC and all those things. You only have this data point. Where do you set this breakpoint? Right. No, you essentially have this. You essentially have the magenta curve, right? You did your experiment and you got this curve. I need to figure out where is that Bode cutoff point.
We can extend this. We can find out what the value and how by 1 times. Yeah, that's what I'm saying.
Okay, but where do you extend? This is a continuously changing slope, right? So do I extend from here? Do I extend from here? It depends on how many data points you have taken them, right? Right? So another critical thing for Bode plot is the fact that if it's a first order system, you look at this, what happens? What is the exact value of Vg over Vi at omega equal to 1 by RC? 1 over root 2, right? And 1 over root 2 is what is essentially at infinite frequency, you are supposed to get 1. At this cutoff frequency, you are supposed to get 1 over root 2, 3 dB lower than what you are supposed to get. So since you have this flat line here, what you have to do is you extrapolate it, that is fine, and then check where this magenta curve hits 1 over root 2, right? So let's say it hits here. Then you say this is 1 over RC, right? So from experiments, even without knowing what are the values of RC, by looking at this frequency response, you will be able to figure out what exactly is the time constant of the system. Then you say that I'll plot it like this. That is my Bode approximation. So this is the frequency response of frequency way of going about, or rather frequency analysis which you can use to go about figuring out the response of a first order system. So in a first order system, so there are two critical things. One is the time constant of the system. The time constant of the system you can figure out by giving a step input and observing the output and see where the output goes to 1 over E of the final value and all those things. In case of this frequency response, you can look at it and say that I will look for a point where the output is 1 over root 2 with respect to, in this particular case, the final value. And then that will be my breakpoint. Now, why is this important for circuit designers? This plot is important because as a designer, you'll have to figure out the values of R's and C's. And if you want your capacitance to be short, right? If you want your capacitance to be short, you ideally want your capacitance to be at infinite value. But infinite value is only a theoretical construct. You cannot go there. So you'll have to live with some finite values of capacitance. Now, if you have to live with a finite value of capacitance, then obviously you incur some error. Now you have to go back and ask, how much error can I tolerate? In case of a first order system in this particular circuit, where I want these two plates to be shorted almost, then obviously I would want the frequency of operation to be on this side of the curve, on right side of the breakpoint. Now, depending upon how much error you can tolerate, you can decide to go set your omega naught to be here or set your omega naught to be here. It depends upon the design constraint. Make sense? But actually, you will do the, whatever I said, you will do the reverse, because I'll be giving you, or somebody will be giving you a system. I'll be giving you omega naught and I'll be asking you to figure out RNC. Right? So that omega naught will not be your choice. The choice will be of RNC. So given an omega naught, then you'll have to push around these breakpoints by changing the values of R's and C's. Make sense? Okay.
You can make it as small.
You can make it as small as possible, but in that case, your values of R and C's can become as high as possible. But then there are practical implications, right? One of which we talked about in the last class. Okay, fine. So this is as far as the input side biasing of my common source amplifier is concerned, using only one battery. Now, also, I mean, in this case, this is RL. That's how we had proceeded. But sometimes what happens is the load resistance will be in the, I mean, in this case, the job of RL is not only to act as a load, but it also acts as a DC biasing case, right? The value of RL also determines what is the value of VD, right? So sometimes what happens is that the load RL, you don't have access to both terminals of RL. Okay, I mean, the load RL might be some next stage that you are driving, and this RL is grounded. So if that is the case, I want to drive signal into this RL, and this RL that you see here is some, it's RD, because that RD's job will be to give me DC biasing. Okay, so this is again another practical situation where one stage of your of the amplifier is trying to drive something, and whatever it's trying to drive has some resistance RL. And as it turns out, let's assume that you don't have access to both terminals of RL, which essentially means that this RL terminal is grounded. So then what do you think? What is the strategy? What should I do to get amplification across RL? Is the question clear?
Where is RL?
I'll just connect it. Quiescent current will change, right? Quiescent current will clearly change. So before I had connected, this current, I would have carefully chosen this bias current IDSQ. This current was flowing through RD, also IDSQ, correct? And let's assume this IDSQ I chose to be 1 milliamp, right? Let's say this is 1 milliamp, 1 milliamp. This RD was, I don't know, maybe 2K, and this is 5 volt. So VD was 3 volt, right? And let's assume this RL also is 1K. That is given to you. I mean, you have to drive. So now I say that I will connect this here, right? I directly connect it here. So what problem do you see?
So why don't we connect?
So the quiescent is clearly changing. In this case, the way I have drawn, it seems like this, if things have to work properly, this has to take in 3 milliamp current. But obviously 3 milliamp current cannot be supported, right? Because if 3 milliamp current has to flow through this 2K resistance, then you need 6 volt of drop, which is not there. So this circuit will simply not work, in the sense that the transistor will go out of saturation. So the moot problem here is, however, in this case, we would want all the incremental current to flow into RL, ideally, right? Because it's the incremental outputs or the inputs that are of necessity. The quiescent condition is necessary for us to ensure that the transistor remains in the right operating region, right? So that is one of the necessary evil we have to deal with. But what we are doing all these things just because we want to pass the incremental current to the load. So this drain has to be connected to RL. Otherwise, the incremental current will not flow. But if I directly connect it, then I have a problem, right? And if I directly connect it, my bias goes for a toss. So I cannot directly connect it. So again, I mean, if I have to argue this from ground up, what am I seeing? I'm seeing that the quiescent voltage VRLQ is 0. That's the problem, right? The quiescent voltage across VRLQ is 0, but the quiescent voltage across VDQ is 3 volt. If I connect these two, I am disturbing the quiescent voltage of VDQ, because the quiescent voltage of the next stage is not equal to the quiescent voltage of the previous stage. If I make the quiescent voltage of the two stages same, then I can obviously connect it, then there will be no quiescent current flowing. So one way to make it same is to say that I'll connect a battery of 3 volt. Then this becomes 3 volt. And I connect these two, no harm done. But by now we know that this battery is not possible, but we have a replacement. What is the replacement? An infinitely large capacitor. All I need to do is to connect an infinitely large capacitor. So this is C1, this is C2. If I do this, the capacitor automatically will get charged to 3 volts, right? Because at steady state, this plate is at 0. At DC, under quiescent condition, that plate is at 0. This plate is at 3 volt. This is even better than a battery. You don't have to figure out what voltage it needs to be. You put in the capacitor, the circuit will decide. The circuit decides what voltage the capacitor needs to be, and it charges both the plates with the necessary voltages. Great. And if C2 tends to infinity, I know that under quiescent condition, under incremental condition, C2 is shorted. So what will be my incremental network under quiescent conditions? Under small signal conditions? The incremental network changes slightly. And what is that change? So this stuff remains as is. Capacitor is shorted. This is R2. This is R1. This is also grounded. This is my VG. This is the source, right? The source was grounded. I had RD. RD is also grounded here. Now what has changed? There is an extra stuff. This capacitor C2 got shorted, and I have, correct? And this becomes GM times VG minus VS, but VS is grounded, so this becomes GM times VG. And my output, which I was supposed to take across RL, I'll still take across RL, and this is what the system will look like. Make sense? So what will be V0 over Vi now? The incremental V0 over Vi? What is VG in terms of Vi? VG is Vi, right? So this is VG is Vi. So what is this current that is flowing through this incremental source? GM times Vi. Where is this current flowing? Into a parallel combination of RD and RL, right? Because both sides of other sides of RD and RL are grounded, right? So this is essentially this. So, and if it goes into a parallel combination of RD and RL, what will be the voltage that will generate into at V0?
So why do you think R1 and R2 are also in parallel? R1 and R2 are also in parallel. Now why would you connect it to one?
Okay, so this is grounded, right? So this is grounded. So it doesn't really matter which ground it goes to, as long as it goes to ground. R1, are you saying that R1 and R2 will load?
Just like R2 is in parallel, R1 and R2 are also in parallel.
Correct. But parallel to what? Okay, so let's do this. So this is 0 volt. 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 It doesn't really matter which 0 volt it goes to. Correct. So essentially, I can redraw this circuit as some current source, which is a value GM times Vi, going into RD and going into RL. And this is grounded. And this is V0. Right? So what is V0 over Vi then? Or rather, what is V0? This is minus GM times Vi, RD. It's there because you have to bias, right? So I cannot. Okay, so that's actually a very good question. His question is, what is the point of RD? Why don't you tell me what is the point of RD? What happens if let's remove RD and short it to? Yeah, fine. That's not so bad. VDQ to be 5 volt, but is there any other implications? No, right? If RD is 0, then this is shorted to, right? All the incremental current will go into the short, nothing will go into RD, right? So your output will always be 0 then. So it's again one of those necessary evils you have to live with, right? So you can ideally, I would like the VDQ to be equal to 5 volt as high as possible, because that gives me good swing limits, right? But if I do that, then all the current flows into the short, it doesn't flow into RD. In the small signal model, right? Okay, fine. So now, obviously, this, which means the gain, the incremental gain is minus GM times RD parallel RL. So clearly you see that there is a compromise here, right? Because ideally I would want the gain to be minus GM times RL, because in the common source amplifier it was GM times RL, but because you have RD, you get this gain will be smaller or higher than what would they have gotten if if let's say I could have attached the load here. So I said that you have a load which whose both terminals are not accessible. That's how we started off. If both terminals were accessible, I could have attached the load in place of RD. And in that case, I would have gotten a gain of minus GM times RD or GM times RL. But because I have a load RL, all the current is now getting split between between RD and RL. And that is why I am getting this parallel combination stuff, right? So this gain obviously is lower than the case when I would have gotten if I had the flexibility of putting RL directly in place of RD, right? So now tell me, if I still want this to be equal to almost equal to, I want, let's say I want almost this to be equal to minus GM times RL. What design choice should I make? RD to be very, very high. Now, if RD is very high, what happens to my quiescent operating conditions? I'll have a lot of drop across the RD, right? I will have a lot of drop across the RD, which means that my transistor will go out of saturation. So if I say that I need RD to be very high, I am flexible with VDD, then what should I do? I should raise VDD to higher value, right? So that is one, you can play around with that in an experimental setup. You can change the VDD and so on and so forth. Okay, so do you agree with the fact that if I have to drive all the incremental current into RL, then and only then I will get an output incremental gain of GM times RL, right? Which means that there is a current division that is happening at the drain. In the incremental sense, there is a current division that is happening here. When the current reaches the drain, it has two paths to take. One is this path, other is this path. So it will always take the low impedance path. Now, low impedance is a relative term, right? So how low depends. So if all the current has to flow into RL, then RD has to be much, much higher than RL. If RD has to be much, much higher than RL, go back to the quiescent state and see what implications it has. For a fixed VDD, if you increase RD, obviously you are then saying that my VDQ or the drain voltage has dropped, which means the transistor likely has gone out of saturation. So, but I don't want to do that, but I still want high RD. What should I do? I should raise VDD, right? So there's one last thought I want to leave with is the fact that what happens if I could, for example, replace RD with a current source? Instead of RD, I put a current source. What happens if I somehow could have said that I will do this? You answer this question, you will know. Let's say I was able to do this. Then in the incremental sense, what will happen? In the incremental sense, the current source will open up and all the current will go into, incremental current will go into RL, right? Because the current source gives you infinite impedance, right? But it need not necessarily be the case. In case of a current source, you need to maintain a large drop. It can have a current source, ideal source can sustain any voltage across it, right? So that is why after mid-sem, when you will see that, we'll try to replace this RD with a current source so that I can still operate with low supply voltages while not compromising on the current division at the output stage. Okay. Okay, fine. Great.